All right, next example. Again, we're solving sine x times tangent x equals 3 sine x for all angles between 0 and 2 pi radians. Again, we're in radians. Make sure you're calculating that to radians. You have to be really careful with this example. Um, so I'll start off with there's a common mistake that a lot of people fall into where they notice that there's a sine x on both sides of the equation and they assume that they can safely divide both sides by sine x, which is technically a legal move. But in this case, what's going to happen is the sine x here and the sine x here are going to simplify to 1. And when that happens, you're going to lose a variable. If you kind of think about this, sine x times tangent x, we have a variable for both of these functions. So this is kind of quadratic in nature, or is quadratic in nature. And when we divide both sides by sine, we're going to lose one of the power of the variable, which is going to eliminate solutions for us, and we can't do that. So in this case, we have to come up with an alternative approach here, right? So what we're going to do is we're going to move all variable terms to one side of the equation, okay? And that's what you would do if this was an algebraic expression, right? If you're trying to solve it and every time you divide, you lose a variable, the best bet is to set it equal to 0 because it is quadratic in nature. So we subtract 3 sine x from both sides, right? And then at this point, you need to evaluate what you're looking at. So again, we have sine x tan x minus 3 sine x. Two terms. Sine x tan x is one term, minus 3 sine x is your second term. Both of these terms contain a factor of sine x. When you notice that, that's an indication that you need to factor, right? So we're going to factor sine x out of this equation, and we'll be left with a factor of sine x and another factor of tangent x minus 3. So let's do that now. And you don't want to factor until it's equal to 0. And once it's factored, we can jump into the zero product property, because if we have sine x times tan x minus 3 equals 0, then one of these factors must be equal to 3. That's the zero product property. So we set each factor we have here equal to 0 and look for all solutions that would make either of these factors equal to 0. So when I do so, sine x equals 0, we're not done with this, but this factor is essentially ready to start finding angle solutions. Over here with this factor, we need to isolate tan x, so I'm going to add 3 to both sides, and then we're going to go into our standard equation solving practice, right? So you want to look at the value of the ratio. In this case, it's positive 3 or 0 in this case, and start determining, what quadrants are our angles located in and taking the inverse sine or tangent if necessary. So let's work off the sine function first. Okay, so this is a unique ratio. It's 0, right? So you want to look for special ratios: 1/2, √3/2, √2/2, positive, -1, or 0. So in this case, sine x is 0. Remember, the sine function is the ratio of the radius, is the ratio of the y coordinate over the radius. If the unit circle is in place, the radius is 1. So we're really just looking where on my unit circle is my y coordinate equal to 0. So our first angle here is 0 radians. Our y coordinate is 0 right here. So we have one solution at 0 radians. Moving around the circle in the positive direction, I find another angle that intersects the circle with a y coordinate of 0. It's right here. So that's going to be pi radians, or 180 degrees. So for this particular factor, sine x, we have two angle solutions, 0 and pi radians. Now we're going to move into solving the second piece, right? So we have tangent x is equal to positive 3. Tangent is positive in quadrants 1 and 3 here. And now 3 is not a special ratio for the tangent function. So what we have to do now is use the inverse tangent function. Again, make sure your calculator is set to radians. So we're going to take the inverse tangent of both sides, and we end up with x is approximately 1.249 radians. Okay. The pi over 2 angle, right, at 90 degrees here, pi over 2 in radians is about 1.5 radians. The angle we just identified is 1.249 approximately 1.2 radians, which makes it a reference angle at the same time. So this is beneficial. We're going to use this reference angle for quadrants 1 and 3 to find our actual angles. So we're going to go into a diagram here. I have a green angle in quadrant 1, a blue angle in quadrant 3, both with the same red reference angle right here. So the first quadrant angle is identical to the reference angle, 1.249 radians. And then for my blue third quadrant angle here, I'm going to add my reference angle of 1.249 to pi radians. Remember, half a rotation is pi radians plus that reference angle gives us 4.3906 radians. Now it's safe to round. And we're going to list our solutions, our angle solutions from least to greatest. So we have 0 radians, 1.25 radians, pi radians, and 4.39 radians. Right. So again, just a quick recap. The tricky part here is, knowing that you should not divide by sine x to eliminate a variable, that you have variables on both sides of the equation, and best scenario here is to set the equation equal to 0, factor, move into the zero product property, and then start solving your equations the same way we did from chapter 7 and chapter 8.